let's try to solve this one together. So at first, they're asking me to find the magnitude of the difference of a complex number. Okay, so let's see that. So it's a magnitude, which is something to do with the Pythagorean identity. So if I have a absolute value of complex number, that's gonna be square root of a squared plus b squared. That's great. And in here, what you can have is a magnitude of cosine 2 pi over 3 minus 1 plus I sine 2 pi over 3 is what you have. So you can do the algebra of square root of the real part square and then the imaginary part square. So that I can put it square plus I can put it as a sine squared over 2 pi over 3. No problem. What you can also do is to remember whenever you do the sum or difference of the complex number, it is good to memorize the following form. The sum of complex number is 2 cosine theta minus phi over 2 cis theta plus phi over 2. So you can memorize this formula. It's always helpful. So that's correct. And what we can do then is to go back to the complex number that we had. I would consider this as a cis form. So this is going to be cis 2 pi over 3 plus cis pi. And then on this one, what we can do is to use the formula that we just learned. But for the addition, I can change the order. So I will do that. And it becomes 2 cosine. You subtract, that's pi over 3 divided by 2, you get pi over 6. And then you have cis, you add, which is 5 pi over 3. You divide it by 2, it becomes 5 pi over 6. So that's it. So as you can see, the magnitude can be calculated much simpler way. So it's going to be 2 times root 3 over 2. So magnitude is simply root 3. That's great. So that was the first question of the problem. Now they are saying that the A, B, C are the vertices on the Argand diagram of a equilateral triangle. So what I like to do is to draw the unit circle like this, okay? And I have a real axis and I have imaginary axis. Okay, that's great. And on this, what I can have is I'm gonna label them. Here it says that the alpha is positioned at z is equal to 1. So I'm gonna put the alpha A here. And since it's equilateral triangle, everything has to be rotated equally. So I'm gonna go to the so this is when z is equal to 1. And I have also another at the 2 pi over 3. And another will be 4 pi over 3. So that's great. Okay, so I have A, B, and C located after 2 pi over 3 rotation. So I've indicated the part B. And then the next question tells me, now the bill wants to go to A. Sorry, A wants to go to bill directly. And then we can figure out the distance using the triangle. And I've got the speed. Hence, they asked me to find the time. And we know time is distance over speed. So what we can do is that we can figure out the distance from A to B, where that is going to be, I'm going to put a perpendicular foot here, and it's a right angle, okay? And then the length I have here is going to be the half of it. So I got the L over 2, and I got the radius of 1. So, which is going to be hypotenuse, and since it's equal to triangle, the angle here will be pi over 3. So I have a right angle triangle like this, where this is a right angle, and this is a pi over 3, and this is the hypotenuse. So the opposite must be sine pi over 3, which is root 3 over 2, and that's L over 2. So you now know, therefore, the length here is going to be square root of 3. So that's great. That's what I have on part C. But that was the length, so I want to find the speed. So I'm going to divide this by the unit speed 1. So we have root 3 unit per second. So that's going to be my, sorry, that was 1 unit per second. And this is going to be unit. So I have a root 3 square root of 3 seconds is going to be the time it took for me to travel to C. Sorry, from A to B. Okay, that was the question answer to part C. So that's great. Now let's have a look at part D. It says A chases Bill, and then Bill chases C, and C chases alpha. It says they all travel with the speed 1 unit per second. The position of alpha at the time t is denoted by ZA. And then the position of Bill will be denoted by ZB. So they are always chasing each other. which is going to create the rotational movement. That is great. So what they're trying to say here is I have my displacement of A indication here. And if you look at the left-hand side, that's a derivative. That's a derivative of Z. That's a derivative of displacement. If you're dealing with the derivative of displacement, that's a velocity. So now they're asking, how do you express the velocity as such? They're asking you to describe the velocity as in terms of this following expression. Okay, so what we do know here is I do know the so if you now go for the numerator, that is a difference of vector ZB minus ZA. So that means I'm going from A to B. That's the direction vector. This is the direction vector. This is the direction vector. And then what we do know here is we do know the speed. For everyone's movement is 1 unit per second. Everyone's speed is 1 unit second. That means the magnitude of the velocity, which is speed, must be 1. Is what I'm given. And when you are doing the kinematics for a vector, remember, if you were given the direction vector, okay, you got to make it as a unit vector. And then you multiply by the speed, which is the magnitude of a velocity vector. That we call it velocity vector. So here what we're going to do is, because I'm given the speed as a 1, and then the direction vector from A to B is ZB minus ZA, but I'm going to divide it by its length, which is going to be the magnitude of this complex number. That will give you the velocity vector. This will give you the velocity vector. So this is a question that goes with the complex number and then the vector, especially for the kinematics. That's great. So that's answering part D. Okay, D is done. Now I want to do part E. Let's move on to part E. They asked me to do the ZB in terms of ZA, but remember, they are chasing each other right now in a circle. Okay, they're chasing each other in a circle. So if you want to get to the complex number of ZB from the ZA, what you can do is you're always going to rotate around. And I do know the rotation, which is going to be 2 pi over 3. So I want to add, for rotation, I want to add the argument. And in the context of a problem, I want to add by 2 pi over 3. But for the complex number, if you want to add the argument, you got to multiply the complex number. So what I can do is my positional vector of B on the Argand diagram is going to be rotating the positional vector of A with cis 2 pi over 3. That would give me the location of ZB according to the rotation. So that's great. That's great. But now they asked me to describe who in terms of Euler form. Okay, so yes, it's okay to write in cis to indicate that it's a rotation, but they're now going to differentiate the complex number. So let's change into the Euler form. So now I have a ZB is equal to ZA e to the power of I 2 pi over 3. That's what we have. And on this one, what they're asking me to do is now if I had the ZA to be the following modulus and then the argument, they asked me to differentiate this with respect to t. But I hope you realize now we have 2 parameters. I've got the parameters of r and I got the parameters of theta. And in fact, they are variable because while rotating, while chasing each other, the angles are changing as well as the modulus. So now I need to do the product rule and the implicit differentiation. So let's try that. So if I do the product rule, I'm going to differentiate the modulus first with respect to t, but it should be implicit. So it's going to be, therefore, dr over dt times e to the power by theta as it is, plus r times, I now have exponential function, so it's going to be the exponential function itself. However, you got to multiply by the derivative of the angle with respect to t by the implicit differentiation. That is great. So I managed to describe the derivative of ZA with respect to time t, no problem. But now let's have a look at part G. Hence, by comparing real and imaginary part, find the differential equation for the dr over dt and the theta over dt. So they're asking you to compare the real part as well as the imaginary part. Well, so what does that mean? Well, let's try to see how we can put this derivative equal to something else. And I believe for that we should also try to use, what is it? The definition, right? So I think the definition of the derivative we already gave was the as you can see, the velocity vector, right? We found the direction vector first. If we divide it by its magnitude, because that will give you the unit vector, and then we multiply by the speed, which happened to be just the 1 unit per second. So that's your velocity vector. And what the question says is that no matter what, even if you got it from vector or you got it from the calculus, in fact, in this case, differentiation, what they should represent is the same thing. What they should represent is the same thing, is what the question is saying. However, right now, I don't like the left-hand side too much because there are too many variables going on. And I think what we are trying to do is, what we are trying to pin down is the expression of the complex number A. So the positional vector for the complex number A. So what you want to do is to use the previous answer on part E, where ZB is just rotated vector from the ZA. So I'm going to replace that. I'm going to replace ZB with the following complex number, minus ZA. Okay, that is great. I'm going to divide this by the magnitude, okay, of the ZB, which was the product of the ZA with this complex number. And I'm going to subtract that by Z. So that's great. So what we can do now is obviously to simplify further. And then the on the numerator, I have ZA. And then it's going to be e to the power of I, 2 pi over 3 minus 1 is what I have. And on the denominator, what I have is here is I can also factorize by the magnitude of ZA. And then it's going to be e to the power of I, 2 pi over 3 minus 1 is what I have on the bottom, right? That is a super nice. But of course, I can give further definition because we described, I believe, the ZA as the modulus and then the following argument. So let's try to put it into the Euler form, especially on the numerator. I can give it as r times e to the power of I theta, no problem. But for the absolute value of complex number, that will be simply just the r. So I have that. So what I can do is I can just cancel it out, right? No problem. So then if you look at the remaining parts is what we have here. And I believe we already calculated the magnitude of e to the power of I, 2 pi over 3 minus 1 in the part A. I believe in the part A, we had to find the answer for the magnitude of this difference of a complex number, which we found it as, I believe, root 3 over 2. So I can use for free. I will use it for free. So now, this is from the part A, it becomes simply just root 3, and that's that. Okay, so far, so good. I'm trying to simplify as much as I can. And so here, and also for that part, we also use the sum of complex number, right? And if I just scroll up just to get that expression, it was this. So I know that the e to the power of 2 pi I over 3 minus 1 will be so for the first one, I have e to the power of I theta times this complex number will be cis 5 pi over 6. But it's important to distinguish the real part, the imaginary part, because I want to compare the other one with the implicit differentiation. So if I try to put this in the cosine and sine, cosine, first of all, I got the magnitude of root 3. Okay, no problem. And then the cosine 5 pi over 6 will be, it's in the second quadrant, so cosine has to be negative. And then the sine will be positive. Okay, that's great. And I'm dividing that by root 3. So it cancels out beautifully. I'm very happy. So now we have the simplified form as e to the power by theta times the following terms. So that is from the vector, right? We try to express the derivative. So the velocity vector, okay, of the complex number in the position vector as a displacement vector as in the Argon diagram. We try to get it as using vector and differentiation. So what you just got is actually from the vector understanding. I try to make it as a velocity vector using the unit vector and speed. But we also differentiated this using the implicit and product rule, which we got it here. Now, even though the expansion method was different, we still should be able to make them equal to each other. So that is lovely. But as you can see, I do see a common vector. The common vector is e to the power of I theta. So I will get rid of it. That is great. I'll get rid of it. That's great. So what you want to do now is to compare the real part as well as the imaginary. So let's try to, where's imaginary part? Is there something that I missed when I was differentiating? Oh, yes. When you were differentiating the exponential with respect to t, not only the d theta over dt, I had to multiply the constant multiple of I. My bad. So I had to multiply the I on that one. It's going to be I here. Okay, so here I should have the I. So now you can compare truly the real part as well as the imaginary part. So if I try with the real part here, I have a dr over dt is, what is it? Negative root 3 over 2. And then the imaginary part will be 1 over 2 is equal to r times d theta over dt. And that is a great. So now you can solve, what is it? Differential equation using this. So the first one is quite trivial, right? So because it's just going to be, well, let's see if I need to solve it or I can leave it as a differential equation. Let's see the question. If I see the question, they ask me to find the differential equation. So I found the differential equation. They didn't ask me to solve yet, so I've got that. Okay, now they ask me to solve it. So let's try to solve it. So the first one will be just integrating with respect to t will be enough. That's great. So then you have the r in terms of t as a negative root 3 over 2t plus c. Okay. And then, of course, to find the particular solution, I need to have initial condition, right? But remember, we were starting with the equilateral triangle, right? And then the vertex A was at the zero argument, right? We had a equilateral triangle like this. So what I'm saying here is the magnitude of A when t is equal to 0, when there is no time spent, it should be 1, right? Because it was a unit circle. So I'm going to add the constant c by 1 is what I have for the expression of the radius. Okay, that's great. Now let's try to solve for the, what is it? The second differential equation, where I believe you should try to, what is it? Put the expression of the r, okay, into the second differential equation. So I replace the r in this way. Okay. That means now I can do the separation of variable. I'm gonna pair the expression of t with dt and then the other expression with theta. Okay, so that's great. So now if I do the separation, I have a 1 over this linear form dt is equal to 2 d theta. And what I'm going to do is simply integrate using the separation of variable. That is great. So what I have on the left-hand side, it's going to be 1 minus this, which will give me the logarithmic expression. So it's going to be ln of absolute value of a 1 minus root 3 over 2t. But remember, it's got the linear case, so the derivative of that will come out as a reciprocal. So I have a negative 2 over root 3. That is great. Plus c1. And then on the right-hand side, it's going to be given by 2 theta plus c2. Okay, so that's great. But, if I put it into common denominator inside, that would be 2 minus root 3 over 2 is what I have. Okay, but I would combine the constant all together. So maybe I would put the C2 on the other left-hand side. It's going to be added together. It's going to give you another constant. That's okay. And then I'm going to divide by 2 on both sides, which will still be the constant. That's okay. But that will be 1. So I have this general solution. This is my general solution. But again, if we now need the initial condition, we are talking about the location of A, and when the time was 0, the radius is 1, and then the argument is 0 because it wasn't landing right on the real axis to the right. So that would be the 0 radius for the initial condition. So I have, if t is equal to 0, I have a negative 1 over 3 ln, and if you put t equal to 0, that's going to be 0. That I've got the 1. Ln 1 is a 0, plus c is equal to 0. So then c has to be 0. Okay, that's great. So now if I go back to the theta expression, that will be simply just without c. So now you got the solution for the radius and then the angle. The radius was this linear progression, and then the angle is given the logarithmic. Okay, so that is great. So we found the the solution for the h. Now let's go for the I. Let's go for the I. It says, how long does it take A to reach B? How far has travel until it reaches B? How many rotations does it take around the origin? Well, so what's happening is this. If I quickly go to the Argand diagram of the picture like this, they are chasing after. All right, they are chasing after. So we initially were set at this location, but as the A is trying to go to the, the Z, sorry, B is going to chase C, but C is going to chase A. So as you can see, the triangle is getting smaller and smaller. But of course, it is rotating, right? And what the question says is, okay, so as you can see, it is rotating, but the gap is getting smaller because of the decreasing nature, right? Of the decreasing nature of the radius. It's going to eventually meet with B, right? So in order to meet, the gap between them has to be 0, okay? So if I now use the radius, the modulus to be the 0, and then t has to be, 2 over root 3, okay? And then that's gonna be the time. Okay, so we found the time, and if it's asking for the how far, that's a distance. And as you know, distance is a product of a time and speed. But I got the time and speed was 1 unit per second. So the distance is going to be 2 over root 3 is what I have. And it says how many rotation does it make around the origin. So, well, if I try to go with t to be 2 over root 3 in my logarithmic function, I got negative 1 over root 3 ln of 0, because 2 minus root 3 times 2 over root 3 over 2 will give you 0. But as inside goes to 0, the logarithmic will diverge to negative infinity, right? From our standard logarithmic function, as you know, the vertical asymptote is at x equal to 0. And as you can see, the y-put is going to the negative infinity. And I'm multiplying the negative infinity with the negative value will make it positive infinity. So, So it says, I need to rotate this infinitely many times. The context you're going to give here is how many rotation do I need? I need infinitely many times because the theta will diverge to positive. So in order for them to meet, they need to rotate on and on and on is the solution for this very nice complex number, kinematics, and the differential equation. Okay, so that was the last question on the holder. Now I'm going to move on to the case of a paper 3 problem. And this question number 4 has appeared in one of the paper 3 problem with the surface area, but this is more elegant and more advanced because you need to actually be able to derive the equation. So let's take a look at that. And let's have a look at the Hayes paper 3 number 4. Okay, so let's try to write down the the formula for the surface area. Okay, so it's going to be something with the calculus and geometry, and hopefully, if so, as you know, it's going to be something with the Riemann sum. It could be something with the Riemann sum of a rectangle. It can be Riemann sum of the sector. Who knows? Okay, it says, all right, so write down the surface area of the curved with the cone of the radius of so I've got the cone with the radius of r and then the height. Okay, so if you expand the network, it's going to look like a sector here, and then the circular base where the arc length will be given by the circumference of the base circle. So the circumference here is going to be 2 pi r, which is going to represent the the arc length here. So that's great. And remember, the sector area is a 1 over 2 r squared theta, or it can be the product of the radius and then the arc length. And since I've got the arc length as a 2 pi r, I'm going to multiply just by r over 2 to the given value. So as you can see, it will be, sorry. So if this is the formula, I then know, all right, the L is the arc length, which is a 2 pi r. And remember, I need to use the radius of that sector, right? So the radius of a circle is not going to be the radius of a sector. And that radius of sector is going to be the slanted height, which I can use the Pythagoras theorem with the h and r. So it's going to be h squared plus r squared. So that's great. That's going to be my radius. Okay. So that's great. That I will multiply, right, onto the, what is it? The radius of a sector. So I got the square root of h squared plus r squared, and then I got to multiply by half. Then boom, I have, what is it? Square root of r squared plus h squared times pi r. So that's 4a. That is great. That's 4a. That is great. Okay, now let's try to go for part B. Okay, so for part B, it says in the diagram alongside, the straight line has revolved around the x-axis to produce a cone. Okay, explain why curved surface area of the cone is not given by this. Okay. So this B1 will be very, very important because it's about the Riemann sum. So here's the thing, okay? I want you to please send me a chat. Okay, I want you to please send me a chat. If I wanted to talk about, okay, area under the curve, what have you used? What shape of a polygon have you used if you wanted to approximate the area under the curve? Yeah, I want someone to tell me, please, on the chat, what geometry we have used for the Riemann sum to approximate the area under the curve and send the limit n to infinity, and hence became the expression of the integral. Yes, what geometry have you used? We use the rectangle. Yes, we used rectangle to, very good. We used rectangle to approximate. Okay, so and then there was a sigma. All right, k is equal to 1 to n function of xk. Okay, delta xk when the n goes to infinity. Okay, and right now, guys, what I want, okay, is to get the surface area of this. I want to get the surface area of this. And what I only know, okay, is to approximate with rectangle is what I know. Okay. So then if I try, to open this network, which is going to be a sector, as we saw from the, opening out the cone, I can maybe try this with the rectangle. Maybe I will have infinitely many rectangle like this. But for the area under the curve, what we had was we had a delta xk, and then the kth x coordinate, we send it to the function. So we had the y value representing the length of the rectangle, where the delta xk will be the width. Okay. So now I wonder what's going to be my width and length. And I believe the width is easier to get because if I had the h height of the sector, okay, what you can do is split that up, right? Maybe I can split this up by the, this is the r, this is the h. And sorry, I think in order to split this up, I'm gonna split up maybe the h. Is it okay? Is it okay to split the h? Yeah, why not? Why not? Let's then make cylinder. Okay, guys, I'm going to make cylinder, just like we got it from the volume of revolution, like this. So in this cylinder, okay, let's say that I have a kth cylinder, which is going to look like this. And this, I claim his curved area is going to be the representation of infinitesimal. That means there are infinite many small shapes of these. Will add up to the surface area of the cone. Okay, let's see if that's truly true. For that, what you realize is that the height is going to be splitting the height of the cone n many times. So that's going to be h over n. That is going to be the height of the cylinder. And now I want to know the, radius of the cone. And for the radius of the cone, what I'm going to do is, that will be the kth x coordinate. Okay. I want to, actually, let me not put it as h yet. Let me call it x first. Okay, so that will be better for me to work with the expression. So let me call it as, it's okay. I think it's okay to call it h, but I will just call it that this is a delta xk, right? That's the gap between the consecutive x. I think that will be all right. Okay, and then what I want to do is onto the kth coordinate, okay, I will put it onto the function here, which I'm going to call it just fx, okay? And he's going to represent me the radius of the cylinder just like we did for the volume of revolution. So this is going to be my function of xk. But remember, I'm not getting the volume. I need to get the curved area. I need to get the curved area of the cylinder. So if I expand, it's going to look like that, where the rectangle's length is going to be given by the circumference, which is 2 pi xk. And then the height was given by delta xk. Okay, that is great. So what I want to do then is to get the rectangle area, which is 2 pi xk. Oh, xk? No, sorry, fxk, right? The radius was, sorry, the function of xk. And that's better. And 2 pi f of xk, delta xk. That's great. And I have many of these. So I'm going to add from my first cylinder to the nth cylinder. And to make the approximation better, I will maybe send n to infinity. Okay, if I did, what happens? This infinite sum will be representing the integral symbol, and I'm going to integrate, in our case, from 0 to h. That is great. And I do have that 2 pi, and I'm going to replace the function just a y, and delta xk, I'll call it dx, is my claim representing the surface area formula of the revolution. Okay, but here's the thing. What we had to show, okay, is that this is not true. What we just derived is incorrect. In fact, what we derived, okay, is an incorrect formula of the Riemann sum. And we had to show why this is incorrect. The reason this is incorrect is the following. I claimed, okay, that this height of, if I get the height of the cylinder, which was a delta xk, but if I were getting infinite many of them, it should represent all features of the cone, okay? I claim it should represent all the features of the cone. If I add all this infinitesimal cylinder, just like the volume of revolution. However, as you know, okay, for the cone, not only is it important for the height and radius, it is important to work with the slanted height. This slanted height is also very important. However, if you add this sort of a rectangular cross-sectional cylinder, if you add infinite many of them in a very small segmentation, would only give you the horizontal distance. It does not represent the slanted distance. So this approximation does not represent the slanted height, which is super important. This slanted height is super important for the curved area of the cone. It is super important for the curved area. So that component is missing. Hence, we do not like it. Okay. So what we need to do in the question is, okay, how can you make it better? Now they're asking me, how can you then, an extra axis has been added along the slanted edge? Yes, because the slanted height is very important for the cone. Explain why the surface area of the curved surface of the cone should be given as such is what they're asking. So now they're asking me to change it. Okay, so now let's go back to the shape again, right? For deriving the integral, it is important for you to work with the infinitesimal shape. But this time, I'm going to give you, I'm going to give you a better rectangle. In fact, I will give you a curved rectangle. I'm going to give you a rectangle that looks like this. That's my approximation for the rectangle. Of course, it's not rectangle. However, if I call this axis S, if delta S is very small, it's going to be approximated as a right rectangle. Okay, so calling out the rectangle, the right angle rectangle wasn't a good approximation, was important in this case. Okay, that's great. So that is gonna be my width for the rectangle. Okay, then I need the length also, which is gonna be the arc length. Okay, so how can we get the arc length is the next step. Okay, so if I have, so now that's gonna be my rectangle. I wanna get the arc length expression. How can I get that? Delta S, I have it. And now I wanna call it AK here. And I wanna find the kth. Well, the introduction of this S-axis can give us maybe the similarity of this cross-section, but I want to do it at one go. how can I find the expression of the, so this is gonna be sk minus 1. That's the length of the radius. This is sk, and this is a sk minus 1. Now, what do we do? I want to find the area. Yeah, the length is r theta. So should I use theta here? But I don't need theta. We will introduce another variable. I don't want it. Arc length. Oh, oh. Yes, the arc length can be done by the circle radius, isn't it? So this is the what is it? The radius r, and let's say we have rk, rk minus 1, etc., for each sk. So that means this arc length, let's say lk, is going to be who? Same as the circumference of the kth radius. So 2 pi rk is the length, arc length of this, which is going to approximate for the length of a rectangle. Okay, that's better. And then for the area of a rectangle is going to be who? Product of this arc length, which is going to be the length of the rectangle, and then this delta xk. Okay, that's great. And I want to add all of them. So to find the surface area, which is going to be the area of a sector, I'm going to add from first term to the nth of this. But of course, I want to make the approximation better. So I'm going to put limit n to infinity. And that's that. So that's great. This is a radius rk. So now what I'm going to do is I'm going to introduce, what is it? Integral symbol. And then we have, what is it? 2 pi r, and then we have ds. Is that the expression we want? No, that's not the expression we want. Where am I missing? I've got 2 pi r, very good. But where have I missed this? Let's go back. So we are trying to find the area using the rectangle. But instead of the right angle rectangle, I made it slanted so that it will cover everything from 0 to s, where the s is going to be the hypotenuse of the right angle here. So I've got the h squared plus r squared square root is going to be the bound. So that I get it. Right? So no problem. So I've got the square root of r squared plus h squared. But where am I missing of the s over square root of r squared plus h squared? Where did that go? This arc length is r 곱하기 theta is sk times theta, right? And that's the radius, that's the angle. But that is the same as who? That is the same as eighth radius, 2 pi rk. Okay, but I don't have rk. That's the imaginary smallest circle here. But I only have the big radius. And for the big radius, it will be used for the entire length. So for the entire length here, it was 2 pi r. But that arc length will be same as the s here. Sorry, this arc length can be described by the radius of the s times the theta. Okay, so now you have expression of theta, which is 2 pi r over s. And this theta can be applied for smaller arc length, no problem. Okay, so far, so good. So on to my expression here, I'm going to put now the sk, and theta was 2 pi r over s. Okay, good. Is 2 pi rk. So now what I can change is, I can get rid of 2 pi. That's great. And I got the r over s, but also I don't have the expression of the s. Instead, I mean, I do, but instead, in the question, they asked me to describe in terms of r and h. So for this s, you can change with the hypotenuse from the right angle triangle. So the s here is square root of r squared plus h squared. Okay, so this s will be replaced by square root of r squared plus h squared. Oh my God, that is great. So I come back to my initial series. So this is correct. This is correct series. But they just didn't want to pair the RK and SK at the same time. So what you want to do is I had the RK initially, but I will get rid of it using the similarity on theta. That is amazing. So now the RK will be replaced by the following, like this. Then I'm going to use the Riemann sum definition. I'm going to be integrating from 0 to, we are using the s-axis, right? We are using the s-axis. So the bounds has to be from 0 to the location of the s, where it could be s, but then now they're asking you to use Pythagoras theorem. So square root of r squared plus h squared is the destination of that integral. And then I have a 2 pi s times r over square root of r squared plus h squared. And this delta s will change to ds. Is the formula that we just derived. Oh my God, that is great. So here what was important is that we were using different rectangle, right? This rectangle would only give you the limit of the r and h, not the s. But now if I introduce a slanted height axis and then use the sector instead of the rectangle, we'll get you the formula that we wanted. That's amazing. Now, okay, so we've got for B1 and B2 correct. Now let's go for part C, because they are now asking you to derive the arc length formula using the Riemann sum, okay? And for this one, they are saying, okay, for the length of slanted height, okay, even if it's a nonlinear, can be approximated using the line segment, right? Because then it's going to be delta S is going to be square root of, it's a small line segment will approximate the length of the S. So what I want to do here is to use the Pythagoras theorem. It's going to be root x. So it's the delta x squared plus delta y squared. That is correct. And of course, I'm going to have an infinite small line segment, and I'm going to add all this. So what we're going to do here is I'm going to add the any kth coordinate. I will have such length, and I'm going to add all of them from 1 to n is what I will have. But your job now is to introduce the integral with respect to x. Okay, you want the integral with respect to x. So if you wanted to have respect to s, you needed the delta s. For the dx, you need the delta x. But I don't have delta x at the moment. So what you want to do is arbitrarily factorize by the delta x squared inside of the bracket. That will give you 1 plus delta y over delta x perfect square like that. And then it's going to come out of who? I have that, and I have that inside of a square root, and this delta x perfect square will come out as a delta xk as it is. But here's the thing, here's the thing. Now this is going to be $1 million question. Of course, to make the approximation better, okay, I would take the limit of n to infinity. If so, I want to get the answer. What's going to be the behavior of delta y over delta x when I'm splitting up many, many times? This rise over run will eventually become the representation of who is my question. I want someone to please send me a message. This rise over run, delta y over delta x, guys, what would that become if I split many, many times? If you split many times, the delta x is getting smaller and smaller. Please tell me. It was like that, but as the gap is getting smaller and smaller, it becomes the gradient of a tangent. And for solving this problem, it was important for us to realize that. So what I'm saying here is this now infinite series will be replacing the integral symbol from a to b, square root of a 1 plus, and this delta y over delta x, which is rise over run, will be replaced by the derivative, because that will be the gradient of a tangent. So we're going to do dy over dx, perfect square dx is going to be the formula for the arc length in this case. So C1, C2 is the derivation of such problem. So we got the part C correct too. All right, very good. And then for part D, if you look, and I believe in the time zone in Europe, okay, guys, time zone in Europe had the question on the ellipse. Okay, I believe it was a paper too. Good to know. And then the so k equal to 1, yeah, just if k equal to 1, that's gonna be just a circle, right? Because it's gonna be x squared plus y squared is equal to 1, then boom, it's good to know the radius is 1, so it's gonna be, pi r. So it's gonna be 2 pi r over 2, so pi r. Okay, so number 2 is okay. But if you look at the number 3, I have x squared over 1 square, again, over 1 square, and plus y squared over 4, right, is equal to 1 is an ellipse. And then they are asking me to find the, what is it? The length of a semi-ellipse, so that's just one above. And we already know the formula. Okay, we already know the formula. So I will be using this formula. And then due to symmetry, what I can do is I can just double it from 0 to r, where r was given to be 1. No problem. Square root of a 1 plus the derivative. We already found it from the implicit differentiation. So it's going to be negative k. So 2x over square root of 1 minus x square dx is going to give you the, what is it, the arc length of the ellipse using the calculator, because they ask you to just use calculator. That's okay. So we're going to move on to the next question. I don't think we are done with this problem, but let me quickly go to the bathroom, and then let's carry on solving this problem together, okay? Are we back? Give me 1 second. Okay, I'm back. If we, the reason we are solving this type of a challenging problem really is to prepare for the paper 3. And I want to show you this question has actually appeared on one of the paper 3 problems. Let me just quickly show you. So, attempting these problems on the textbook will definitely enhance your chance to have seen these problems already. So this was in November 2022, paper 3, regarding with the surface area, right? So as you can see, oh my God, it was about the circle, and then we had to do the implicit differentiation and then use this formula to find it. And that's exactly what we just did for the ellipse above, right? So please attempt those problems in the textbook, right? There are many questions that has not appeared yet. But anyways, if we carry on, I believe we are not done with this problem. The function blah, blah, blah is explain why the surface area of the curve will be given as such. Okay, so now you guys know, all right? Now you guys know. Now you guys know it is important. It is important to work with the Riemann sum, right? So for the surface area of revolution, we already had the Riemann sum expression before. So let me quickly get there. The Riemann sum expression that we derived was these, okay? These were what we had before, understood? But what we are, so this was we had two parts of Riemann sum. The first one was the surface area in the s-axis, but we also found the Riemann sum for the s, which is the arc length of a function, which was, I believe, this. So these two were the main boss of the Riemann sum of this question. So what I want to do is to replace them, right? Replace the value that I can, I can substitute the values and then try to change the axis into the x instead of s. So if you take a look, all right, what we already had is this expression for the s. Remember, this is for the s. Okay, so then in our Riemann sum before, I would change the sk. I would change the sk with this following expression. So it would be, what is it? sk will be square root of 1 plus d delta y k over delta xk squared delta xk. That is going to be the same as what we had before, which had, this is the surface area of revolution. And then I'm going to have 2 pi r over root r squared plus h squared. And I'm going to change the sk with this. Oops, sorry. That is sk. Okay, but I also had the delta xk. So I only changed that. 2 pi r root 2 r squared plus h, okay, sk, and then delta sk, and I like delta xk, but I don't like delta sk. And if you go to the formula, these are the expression that I need. So if I see the ones that are matching, right, I do have delta xk, which will become dx, no problem. I got this square root form, I got that, no problem. I got the 2 pi also. So what is left over is to show this is the same as the function of xk. Okay, how can we show that? How can we show that this is same as a function of xk? 아닌가? Is what we had. Oh, this is not sk. This is a delta s. This should be delta s, I believe. Yeah, this is the delta s. So if I change that here, then this should be yk, sk. Okay. Now it makes sense. Okay, so forget about what I just said. Boom, gone. Okay. This is not sk, but delta sk. This was for the difference. This was for the difference using the Pythagoras theorem. Okay, now it's better. So on that one, I had infinite series of 2 pi, okay? And then this, whatever the expression we have, okay? And then the delta sk will be replaced by this. That's great. But let me quickly remind you the relation between sk and then the r over square root of r squared plus h squared. If you scroll up, we had the picture already, okay? These were picture of the cone that we used, okay? And if you look, the r is the opposite from this right angle triangle. And this square root of r squared plus h squared is a hypotenuse. So if you ask me, what trig ratio can you link with is the sine. So I can have a sine theta is a r over square root of r squared plus h squared. That's a sine theta. But now that can, using the similarity now, look at this. This is a large triangle, but I'm going to go now smaller triangle, okay? Now I'm going to go smaller triangle. The ratio must be the same, okay? And this is going to be, if I call it kth coordinate, if I put it onto the function, that would be f of xk, right? That's the f of xk, no problem. And this will be the kth arc length. Okay, so even though the length changed, because of a similarity, ratio must be the same. I should have this as function of xk over sk. With that understanding, you realize that this ratio times sk becomes function of xk. Therefore, in this arc length formula, I can change the box into the function of xk. Okay, that is so great because now I can change everything in terms of x. I'm going to integrate from 0 to h because there was the bound in this case, let's say. And then I'm going to go 2 pi. The f of xk will just become function of x times the arc length formula, 1 plus f prime x squared times dx is going to be the correct arc length formula for the surface area. Sorry, this is the correct formula for the surface area of 3D revolution, which did indeed appeared on November 2022. But our question from the textbook focuses more on how to derive it using the Riemann sum. So please take a good look at it again after the lesson, because I don't think this is something you can swallow and digest right away. But please know the distinction between the the rectangular versus sector approach we did in this question number 4. So beautiful question. Let's have a look at the question number 5 on the Hayes for the paper 3 problem. Okay. So let's take a look at 5a. Okay. So this is going to be second order differential equation, right? Okay. A given real value of Basel's functions are labeled of J. And then for part A, show that is a solution. So if you want to verify, you're not finding a solution, you already have a solution. They ask you to verify. What you want to do is simply just put this. Sorry, if it's you can use for free, no problem. But I need to show that any constant multiple of J is also a solution. Okay, so what I can do here is I do know that if I let Y to be J alpha over X, it should make this to be 0, because that's the definition of solution for the differential equation. So this works. So for part A, what you can do is you can arbitrarily make another function, but this time constant multiple, okay? Constant multiple of the solution and plug it in, right? And I believe if you plug it in, you're gonna get the same multiple of lambda, because for the derivative, if you have a constant times the function, constant coefficient preserves. So we are using that property. So it's going to be lambda x squared, and then the second derivative plus lambda x times first derivative and then plus lambda x squared minus alpha squared of the solution is equal to 0. So then I can get rid of lambda on both sides because lambda is a non-zero constant. Then I know the constant multiple will be our solution. Okay, easy peasy, lemon squeezy. It's just using the property of differentiation. So let's have a look at part B. The part B shows, it suggests that the for half is also a solution to the differential equation for alpha being 1/2. So for this one, it's really just checking on your differentiation skills. Meaning what you want to do here is, as you can see, for my second order differential equation, you will have to do a lot of substitution, especially the ones you're going to struggle is literally plugging in the solution, right? And now you got to put the first derivative of solution. That means you need to differentiate this once, right? That can be a bummer. So, but if I just do once, I'm gonna have a j prime of 1/2 of x. I'm gonna use the product rule first. So 2 over pi x, and then negative 2 over pi x squared times the sine x, plus square root of 2 over pi x times cosine x, right? And then you do the second derivative. Oh my God, as you can see, it's gonna be very painful, yet it's not that bad because it's not something that we got to use deductive thinking. For part B is checking on your algebra skill. That's part B, okay? That's great. And let's have a look at part C. Given that there is a solution to the differential equation of that, show that is a solution to the differential equation for alpha equal to 1. Well, I guess, the C is going to be also a, what is it? The checking with your differentiation skills, okay? But let's see what we mean by solution, okay? So this is the differential equation that we had. And now I know J naught of a 0 is a solution. And his first derivative happens to be the negative J1. So since it's a solution, I can plug it in first. So using the given information, it's going to be x squared, okay? J1, sorry, J0 second derivative, J0 first derivative, x squared minus 8 alpha squared of J0, okay? That's what we have. But now, for showing that J1 is also a solution, what do you think I'm going to do? Yes, I'm going to see, okay, so I know that this is equal to 0, but what I do not know, all right? What I do not know is if I put J1, so let me just duplicate this. I don't know if it's a 0. That is not confirmed yet. So that you got to show. So that means you're going to start with the left-hand side first. You're going to start with the left-hand side like this. I cannot assume that it's a 0 because that's my aim. But here, what property are you going to use? Yes, you're going to use the property of the fact that the J1 is first derivative of J naught. So I'll try to use it. So in this case, oops, hold on a sec. I think it's x times. Yeah. So this should be x times also. So here what I can do is I can re-express this as for J1 will be the minus negative of this of J naught prime x. Okay. And if you differentiate the given identity, you get the second derivative of J naught. So I'm going to have minus x J naught second derivative of x. Okay. And also, what do we have? The second derivative of J1 will be the third derivative. So I have a minus x squared J naught third derivative of x. So I can convert that in this manner. But what we can do is, so I need to solve it, right? So I cannot let this to be equal to 0. Where else can I come up with this expression? What alternative can we make? Is that, if you differentiate the J0, you get J1. At first, I only use substitution. So this is only by substitution. But you can introduce the derivative by directly differentiating. I only used, again, let me repeat, the substitution. But I think I know I can differentiate the original form of a J0 to get J1. So if I now go back to the equation that I had onto this, so that's going to be the second version of the equation in terms of J1, is that I'm going to differentiate this. And if you ask me why, because the derivative has relation to the J1. I need to convert this form into J1. So therefore, you can expand the left-hand side using the product rule. So that will be 2x prime plus x squared j naught third derivative plus j naught prime plus x j naught double prime 2x j naught plus x squared minus alpha squared j naught prime is equal to 0 is what I have. But of course, at the moment, I don't like it because the whole point of doing this is so that I have expression of J1. And to do so, what you can do is to use this identity. Well, however, I think it's always the best if you could, simplify, right? I think it would be always the best if you can simplify. Who can we simplify? And also remember, if we had, this was given, right? We were given this. And then let's see any other conditions. Alpha is a 0. Okay. In the question, alpha was a 0. So I can actually disregard the alpha here. It will be just x squared for the coefficient of j naught. Okay. That's not a problem. And this is the equation that I got from the derivative. So if I could make whole chunk of the expression to be 0, I'll be happy. So in the derivative, let's try to see if there are some terms that I can actually make 0 instantly from the given identity. Well, I do have, that's third derivative. Do I have x squared? Do I have x squared j prime? No, I don't. I only have, for the second derivative, it's matched with 2x. Okay, still, I like it. For the j1, I have it here. For the j naught, I have here. And then the rest are these. Again, I don't know if this is, sorry, I do know that this is equal to 0 because that was just a differentiating of the given identity. This is equal to 0. And if you look at the equation, okay, I have first 3 terms and last 3 terms. And if you look at this circle one, which number will be related to my given information? Would you apply this highlighted part on number 1 or number 2 is my question. It's a 50-50. I want everyone to please tell me and participate. Would you use that information on number 1 or number 2 is the question. Number 1, okay, 1 vote. Please vote more. 1, 50-50. Yeah, it is actually on number 2. And the reason being is that if you look at our given identity, they are made out of the second, first, and just this function. But here I have a third, second, first. I cannot use it directly, but rather I can use it here. But you're right. I don't like the fact that it's got, the x values are different, okay? So what you can do, okay, is arbitrarily make the x value, right? So what I want you to do is for the second one, I think we can make it similar by multiplying the x. But of course, I need to divide by the x because it wasn't the initial term. So essentially, I'm multiplying by the 1. However, if this is multiplied on the function, I have 1 over x outside. Then I have 2x squared j naught double prime. X j naught prime. 2x squared j naught is what I have. Okay. But here's the thing, this doesn't make everything match. What I also need is the same coefficient. But I've got coefficient of a 2, 1, 2. So what you're going to do now is you can raise the coefficient as a 2, but you will subtract by that term here arbitrarily, just like when you were doing the completing the square, okay, for the quadratics. Aha. So in that case, I have now if I look at just the first 3 terms, now it's got the common factor of 2. So it's going to be 2 over x of x squared, x, and x squared again. So that's great. However, as you know, this last term must be multiplied separately and expanded out will give you negative j naught prime. Okay, that is what we have. But what's the benefit of it? Well, because of the given identity, the first 3 here will actually become 0. And I'm very happy with that. Aha, so we had the humongous terms here after the differentiation and product rule. But in fact, for the last 3 terms, we'll just give you negative. It will just give you negative j naught prime. That is great. So what you can do now is that this is the term we have, and my enemy is the first 3 terms. How can we change that? Well, what we can do is we can bring up, there were two ways of using our identity. So left hand side was this. Give me one second. What were we doing? So this was the given identity. And because of that identity, I wanted to show that this is true. But if you look at, what is it? Okay, so now I need to introduce J1, right? Because we wanted to show that J1 is also a solution if it was negative derivative. So J1 is first derivative negative. So for example, this can be put it back into the negative. J naught prime will be negative J1. So for the first three terms will be converted into negative x squared J1. Okay. J naught second derivative will be negative J1 first derivative. So I'm going to have a negative x J1 first derivative. Like similarly, I'm going to do negative x squared J naught second derivative. Okay. But remember, we were adding by who? We had the negative J naught here, which will be, sorry, negative J naught derivative is there, which is positive J1x. Okay. So with this, what we realize is that, well, this was a 0. And if you multiply by the negative, I have positive, 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 negative is equal to 0. And for these two terms, if you factorize by J1, it will be x squared minus 1 J1 is showing that this time, if this is the solution, then alpha is 1 will be the answer for part C. As you can see, it is not about finding a breakthrough of solving this problem, but instead for part C, what you had to do was to not mess up the equations and be able to put it as tight as possible. So that was very important for part C. Okay, let's move on to part D. So now it's, they say blah, 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 all the real life practical application of this differential equation. Okay, so that they are saying your solution has the following Maclaurin series, where I guess our job is going to follow, to find the coefficient. And when you see a differential equation with the infinite series, it's very likely it's going to compare the coefficient and work with the recurrence relation. It's going to be something with the recurrence relation. Okay, let's see. So if you want to show part D, of course, we can use the differential equation. We were given as such. So what we can do is that we are going to put this in the first derivative and the second derivative, work with the coefficient. So however, here's the thing, you got to be very careful when you're working with the infinite series and differentiation is that if you had a constant term, if you differentiate, it disappears. So let me show you what I mean by that. My Jn of x is given to be sigma ak xk. When k goes from 0 to infinity, suggesting I start with the constant term. But if you differentiate the power series, and remember we had a constant term here, and it would be a1x, a2x squared, goes on and on and on. If you differentiate, I get a1 plus 2 a2x, 3 a3x squared, on and on and on. And of course, we want to put that as a sigma form. So this is going to be starting from k equal to 1 to infinity of k times ak times x to the power of k minus 1. I want you to notice that the index changed because I don't want to deal with the disappeared term. Right? A naught has disappeared. So that's great. But we don't like this because every time you're working with the infinite series and differential equation, you really want to match the power as x to the power of k. So you got to change the index of sigma. How do we change the index of sigma? This is going to be k. So I'm going to arbitrarily make as x to the power of k. And when you put k equal to 1, it became 0. So then if I arbitrarily change to k has to start from 0 to infinity. But as you can see, I raised k by 1, so everything else here must be raised by 1. That is typical notation for the first derivative of your general solution of the Maclaurin series. Likewise, if you do the second derivative, I'm going to just differentiate this as it is using the power rule, but please also make sure that you realize that I need to reduce the number of terms by 1. And then it's going to be k times x to the power of k minus 1 again if I do the term by term differentiation. But I don't like the fact that I have k minus 1 there. So I'm going to change x to the power of k. Everything will be raised by 1. So it's going to be k plus 1, k plus 2 times a k plus 2, starting from k is equal to 0 to infinity. This way, it's easier for you to compare the coefficients. Okay. So now I've got all the list. So we have this general solution term and the first derivative version with the power of k within the sigma, and then the second derivative version. So these are the three forms, three expressions that we're going to use for solving the differential equation using the Maclaurin series. Okay, so now I need to put that into this differential equation. Okay, let's try. So what we have is we're gonna multiply by the x squared on the second derivative, which I have it here, and I'm gonna multiply this by x times the first derivative. That's great. And then the last term will be multiplied by x squared minus alpha squared. The general solution here was y, so I have that. And we were given this to be equal to 0. However, this is not the end of it, because if you want to simplify your differential equation, you need to make sure your power must match. But at the moment, it does not match, because now multiplying the x squared and x will raise the power. So let's simplify further. I've got the x to the power of k plus 1, sorry, k plus 2. And then this will raise by 1 for the second term. That's great. And for the last term, I guess you have to do the distribution here, right? So make sure you do the distribution there. Oh, are we given the alpha value here? Maybe you can simplify it. Are we given the alpha? No, we are not given the alpha. Okay, so then it's gonna be raising the power by 2 for the first term within the bracket. So I'm gonna add this x to the power of k plus 2. All right. Then I have minus alpha squared and then the sigma. And the only term that is good for solving the general term of the Maclaurin series is anything with the power of k. So this is the only good option at the moment, and we don't like it because the rest I have to change it. Okay, so let's see how we can change, for example, of this sigma here. Remember, I'm going to arbitrarily just put x to the power of k because that's what we prefer. But for that one, now you realize it has to be reduced by 2. So the a will be ak minus 2 for the coefficient. So now if I put 0, I started with the quadratic. So your k now has to start with 2. That's what's happening. Okay, that's great. Now let's have a look at this one. Okay, we still don't like it because it's to the power of k plus 1. So I'm going to now arbitrarily put x to the power of k. If I've done it, got to reduce by 1, then it's going to be just k times ak. But remember, in the initial sigma, the index started with 0. That will give you a linear term. So for this one, to start with the linear term also, I'm going to go with k equal to 1 to infinity. That's important to start. Okay. Now, I'm going to go with the, this term here. Again, I don't like the to the power of k plus 2. So I'm going to put x to the power of k. So I'm going to reduce by 2 on each term. So I have a k minus 1 and k. And this way, I start at where? If you put k equal to 0, I'm going to start with the quadratic. So I'm going to go from k equal to 2 to infinity. And that is the generalization for the power of k. So this was our this was our initial form, but I'm going to now make it nicer so that everyone has the power of k. Here, the second term was this one, I believe, yes. And then the last term was this. Yep. And then the second last term was that. And then the last term is left as it is. So that's great. So we have add, and subtract. Okay, that's great. But whole point of doing this is so that everything can be put into the power of k. However, here's a problem. If you look closely to the given equation, this starts with quadratic term. This starts with linear term. This starts with the quadratic term. This, however, starts with the constant term. So if you tell me the intersection of the power to describe should start with the quadratic. So the way that I can put all this sigma together within one sigma is when you start with the k equal to 2. So I'm going to start with sigma k is equal to 2 to infinity so that I can put everything within the sigma. The first term was given as it is, no problem. So I'm going to just extract the coefficient, no problem. That's going to be k times k minus 1. Okay. Oh, where did the ak go? Yeah, it should have ak, right? Thank you. So I have ak here. And then the second one started with the, what is it? The linear term. So while I'm putting the, what is it? The expression of the sigma, I mean, so the sequence within the sigma here, you need to realize I start with the quadratic. So it's a linear term must be added outside. So if you put k equal to 1, it's going to be 1 times a1 times x. That's the linear term that should be left out within the sigma because I'm trying to describe starting with the quadratic. Okay, that's great. And that is starting with the quadratic, so it's okay to use ak minus 2 right away. Sorry, I'll get rid of xk because I'm going to multiply that at the end anyways. And I'm going to add that here, okay? And then on this one, you realize, okay, it starts with 0. That means it starts with the constant term. So I can definitely put the minus alpha squared times ak and then put everything here for the x12k, no problem. However, its linear term and constant term must be still added outside. Okay, so its constant term is when k is equal to 0. So I have a minus alpha squared a0. And when k is equal to 1, it cannot be put into the sigma. So I'm going to put minus alpha squared a1x. Okay, that is what we have so far. That's great. That is great. All right. So now what are we going to do? Let's try to simplify anything within. So here, okay, I have a constant term, which is a negative alpha squared, a naught. Okay. And then the linear term will be simplified as plus ak minus alpha squared a1 is the linear term, which cannot be put into the sigma. And the sigma here, I think what you can combine is the common factor of maybe the ak. So I have a sigma k is equal to 2 to infinity, okay? And if you factorize by ak, then what you get here is k squared minus k, that's just expanding of this term, plus k minus alpha squared. Okay, so k cancels out. And I've got the minus alpha squared, ak, that's great. Plus ak minus 2 will be the coefficient for the x to the power of k within this sigma. And they tell me is equal to 0. And let's see if this truly matches to our claim. And yes, it does. Okay. Oh, by the way, they said the alpha, we usually have a j alpha of x, but they have given me, it was n. So you can replace the, what is it? The alpha with n. No problem. N. In this case, it's going to be n, and then what else? Alpha will be replaced by n here. So as you can see, all the coefficients match. It's beautiful, right? This is what you have to show, right? By changing the power to the power of k. So we did show part D, okay? So explain why the first of the series expansion is the x to the power of n. Explain why the first term in the Maclaurin series expansion for Jn is x to the power of n. Okay, what does that mean? Let's read it carefully. Let's have a look at the part E. So, you know, what you do know is everything here, okay, must become 0. So then you're going to solve one by one, right? What I mean by that is for n to be a natural number, as you can see, negative n squared a naught has to be 1. For if it was a non-zero positive integer, this suggests a naught has to be 0. Okay. And now for the second term, we have a 1 minus n squared a1x, unless n is 1, all right, unless n is 1, this to be 0, comparing to the right-hand side, a1 has to be 0. Okay, that's great. So I now have two initial conditions that a naught and a1 are 0. Okay, then let's now go for the sigma, because in fact, this sigma should also become 0. That means I know the coefficient of x to the power of k must be 0. And this is your recurrence relation. This is your recurrence relation because now your present term depends on the two preceding terms. So ak minus 2, I rearrange to the other side, becomes negative over k squared minus n squared. Okay, that's great. So now I want to see any pattern on it because I now have two initial conditions. You can now start with A2. So now I'm going to start with A2, where you know A2 is going to be who? Depend on A naught. All right, over what is it? 2 squared minus n squared. And because A naught was a 0, will become 0. And in fact, if A0 was a 0, A2 is going to be 0, and A4 is going to be 0. It goes on and on and on. So in fact, A0 was a 0, A2 will be 0, A4 will be 0 then, because A4 will depend on the A2, and then every even term will actually become 0. Unless, all right, unless it's K, N is equal to K. So Kn cannot be K. What about odd? If I now go for the A3, which will depend A1, then I have a 1 squared minus n squared, doesn't matter. A1 was a 0. So in fact, like the even case, every odd term will actually become 0. Unless n is equal to k. It cannot be there because even if this is a 0, if n was a k, it will give you 0, which is 0 over 0. That's the case of what? Indeterminate. We don't want to have it. So only term that will have a non-zero or in fact a defined term should be when k is equal to n, because any other term will become 0. Therefore, the question says we had to show it is only available term is x to the power of n. And if nth term is available, right? If an is non-zero, then an plus 2, an plus 4, an plus 6 will be non-zero because he will depend on the an. It was non-zero. He will have some value. He will depend on him, but this depend on him. It was non-zero, will be non-zero values. So that is great. So I know starting with the nth term will be the Maclaurin series of this. Okay, that is great. Okay, that is great. Okay, so now let's go back. So we show the part E. Okay, explain why it's odd function if n is odd and even function if n is even. Well, yeah, there you go, right? Because we said now every two terms after will be the coefficient, and if an was even, and the next term that will be non-zero is 2 terms after, that's still even. Same thing for the odd. So we know it's either going to be bunch of even or bunch of odd. This determines whether the function is even function or odd function. So f is also done by that realization from the recurrence relation. So that's great. So we got the E and F. Let's have a look at part G. Now they're saying we define J naught as a solution to the differential equation for which this is equal to 1. J0 of a 0 is 1. Use a result from part D to show the Maclaurin series is this. What was the answer that we had to use? Okay, so we had to use this. And remember, if J naught of x was the solution, then J naught of a 0 represents for the constant. So J naught of a 1 is A naught, which is given as 1. That is great. And now I know, because of the recurrence relation that we solved before, right, which we had it here, and I had the even term, suggesting my J naught of x must be an even function. Now let's try to find the pattern. Here n is a 0, so then my recurrence relation can be reduced down to negative ak minus 2 over k squared. Okay, that's great. Then we started with what is it? A naught was 1, but since it's even function, our term should be 0. Okay, that's great. So now I'm interested in A2, which is going to depend on the A naught. So minus A naught over 2 square, that's negative 1 over 2 square. Okay, now I'm going to obviously go to the A4 because A3, which is odd term, will become 0 for the even function. So I'm going to go for A4, which then will be minus A2 over 4 square. So that's going to be same as positive 1 over 2 square, 4 square. Okay, so we see the pattern. This is going to be, so A6 is going to be minus 1 over 6 square, I believe, right? And 4 square and 2 square. Okay, that's great. So the pattern that we see here is, these are the even numbers, so it's going to be 2 square, 2 square times 2 square, 1 square. And these consecutive integers can be put into the factorial. So that's going to be, now if I put the power together, that's going to be 4. Is it 4? 2 square. Oh, 2 squared. Yes, it should be 2. Yeah. Yeah, that's better. And no, isn't it? Because I was thinking maybe trying to derive factorial, right? Because 4 times 2 squared, which is 2 squared times 2 times 1 squared. So that's gonna be 2 to the power 4, 2 factorial. Yes. So 2 to the power 4 times 2 factorial is A4. And we smell the factorial for the A6 also. So it's gonna be minus 6, 4, 2 squared. Then it's gonna be 8, 3 factorial square. So we have a negative 1 over 8 square, 3 factorial square. Oh, should be square here. Okay. So now let's try to see the pattern. So now we have A2 is negative 1 over 2 square. A4 is a positive. Well, but for A4, I'm going to write 2 times 2. 2, I'm going to write 2 times 1. It's going to be positive, all right, of this. And A6 is A2 times 3, which is a negative 1 over, okay? And for this one is a 2 to the power 3 to the power 2, so it's a 2 to the power 6 times 3 factorial square. And you can see the pattern, right? And we know we are only interested in even terms, so it's going to be A to N should be. It is an alternating term, so I'm going to write it as, what is it? Minus 1 to the power of N times 1 over, as you can see, it follows the power of that. So I'm going to do 2 to the power of 2n. And for the quotient after factorizing by 2 will represent for the factorial. So I'm going to have n factorial square is the general coefficient that I think I'm going to have for my Maclaurin series. So if I were to express the J naught of x, but remember this starting for n bigger than or equal to 1, it does not account for the initial condition. Initial condition doesn't have to come from the recurrence relation. Remember, the A naught was 1, I believe. So here, if I try to put this on the Maclaurin series, initial term will represent for the constant term, we have 1 plus sigma. N is equal to 1 to infinity. A to n will be then the coefficient of x to the power of 2n. Okay. So then that coefficient A of 2n will be replacing this of x to the power of 2n. And that will be the particular. That will be the particular solution of J naught of n using the recurrence relation, converting into the explicit formula. But for that, you should be able to play around for the first few terms and see if we find any pattern recognition. Okay, is the important part of the part G. Okay, hence write down the Maclaurin series of J1. I think I can use this, right? Because we said that it is a derivative. So I believe you should just be able to differentiate the infinite series that you got. And as you can see, I'm sure if I do the term by term differentiation, I'll be introducing an odd function, which we know is what we proved, right? So J1 will be the negative of the derivative of the solution that we found. And as you can see, the 1 will disappear because it's constant. So I'm going to have a minus, and I'm going to differentiate this. So it's going to be, I don't have constant term there. So even if you differentiate, I don't think it's going to change the index. Okay, that's great. So the coefficient remains the same. And then I'm going to differentiate this with respect to x by the term by term differentiation. So it's going to be 2m x to the power of 2m minus 1 is what you have, right? And that will be the particular solution for the J1. So that's great. So use your technology to generate the 8th order of the Maclaurin series of the J0. Okay, so let's try to do that. Why not? So for the finale of the problem, we found the general solution of the J0. That's great, but they asked me to describe for the 8th order. That means to the power of 8. That means for here, m is not going to go for the 8. It's going to just go up to 4 because we had x to the power of 2m, right? So if you put m equal to 4, you can get the degree 8 polynomial. So I'm going to put that on my calculator because they asked me to sketch. So I'm going to go for the graph here, and I'm going to first set the domain. I'm going to go for manifold 1, and the domain on the calculator. On the question, it says to define from 0 to 6. I've done that. And here, I'm going to put a sigma notation for the series of the polynomial. So I'm going to go with the n is equal to 1. Sorry, I think I should have added my initial term of a 1, and then 1 to 4 of this series. So it's going to be minus 1 to the power of n. You don't necessarily have to put n, but you could, of course, why not? 4 to the power of n times n factorial square times x to the power of 2n. I want you to notice I'm trying to put every multiplication whenever you have to write the terms in a row, because it could sometimes cause an error. So I'm going to press enter here, but I want to make the function more fitting. So I'm going to do menu 4a for the case of zoom fit. So that is my graph. That's my graph. So let's see what the question was asking about after sketching. Okay, so sketch the polynomial. Okay, I did. Hence, estimate the first two zeros of the polynomial. So, yep, that one and that one. And compare your answer with the first two zeros of the node, which are boom, boom for the fourth signal. Yeah, I guess you just have to find the roots and then give maybe the percentage error. Okay. But what you know is for the Maclaurin series, it's the derivative, the coefficient is defined at the derivative at 0. Okay. We call the x equal to 0 is a center of the Maclaurin series. And for the general case of x equal to a, that's called Taylor series. But when you have an approximation close to 0, then your Maclaurin series doesn't have to be expanded. Meaning, if you were compare the sine x with x, they will give you a very, very close value, very, very close value when x is very close to 0. If I quickly show you, sine of 0.001 is going to be same as 0.001. But of course, if sine is further from 0, let's say sine 1, it's not going to be same as 1. So closer to 0, less expansion you have to do. But if further the x, more expansion you have to do. Meaning, if you see your x-intercept, if you ask me what's going to be more accurate, but of course, the one that is close to 0 is going to be more accurate because that's the principle of the Maclaurin series. You're trying to evaluate around the 0. That's why you're putting the derivative. That's why you're putting the 0 to the derivative for finding the coefficient. So the ones that are further from 0 will be less accurate. Okay, is the comment that you have to give for part H. But as you can see, we solved several problems here. Within 2 hours, we solved 3 exam questions. So that's sort of the pace you're expecting, right? Right now, for 2 hours, we solved 1, 2, 3. And you might have felt that, wow, this was so fast, but it wasn't, right? We just managed 3 questions. So we were slower than expected. So for paper 3, what's important is you already have seen the problem. That's the most important. That's really being lucky is the key thing here. If not, still being able to deduce the clue from the previous part of the problem is important. So for that, I strongly encourage you to keep practicing with the paper 3 problems from the textbook. And if you have done that, you can then try to solve paper 3 problems from Wuhan. I think that's more than enough. Only 25 set of 25 questions, but very challenging. But with that practice, I think I'm very certain that you will do a lot better. Okay, so please continue to revise. If you have some questions, please drop me a message. I'll be very happy to help. That's for me today. See you next time.